Imagine a universe completely devoid of mass. It is a haunting thought, a reality where light no longer travels at a finite speed because there is no matter to hinder its progress. In such a realm, stars could never form, for there would be no gravity to gather swirling gas and dust into celestial hearths. Planets would never coalesce, and life, as we know it, would be an impossibility. We ourselves would cease to exist, as every single atom that builds our bodies carries the indelible mark of mass at its very core. Mass is a physical quantity we take for granted in our daily lives, from the simple act of picking up an apple to feeling the steady pull of the earth beneath our feet. It affects our world every moment, appearing simple on the surface yet serving as the fundamental property that constructs all things and dictates the evolutionary trajectory of the entire cosmos. It is the cornerstone upon which the structure of the universe is maintained. Without mass, the universe would be nothing but an empty void, a hollow concept, where no entity could exist or interact. Mass gives matter its sense of reality. It is the condensed form of energy and the essential pillar supporting the grand edifice of space and time. However, the true nature of mass is far more complex than our everyday experiences might suggest. It is not merely a measure of how much substance an object contains, but rather one of the most profound and fascinating mysteries in all of physics. This is a long story, one we might dream about, but before we dive deeper, please remember to like, follow, and share this content. From the microscopic world of fundamental particles like quarks and electrons and how they acquire their mass, to the macroscopic scale of galaxies shaped by the mysterious presence of dark matter and dark energy, mass manifests in various forms. Its origins and the mechanisms through which it operates remain at the heart of modern physics' greatest unsolved puzzles. Scientists tirelessly explore this mystery, peeling back layers from the quantum world to the vast expanses of general relativity. Understanding mass is not just about refining our knowledge of physical laws, it is a gateway to a new realm of physics that could answer ultimate questions about the origin, evolution, and final fate of our universe. Our journey into the essence of mass begins with our earliest intuitions, tracing back to the classical mechanics of Isaac Newton. In the 17th century, Newton elevated mass to a rigorous scientific concept, defining it through the dual lens of inertia and gravitation. Inertial mass, as described in his second law, dictates that the more mass an object has, the harder it is to change its state of motion. We feel this when we try to push a heavy truck compared to an empty cart. The truck's greater inertia makes it much more resistant to acceleration. Simultaneously, Newton's law of universal gravitation revealed that every object in the universe attracts every other object with a force proportional to their masses. Here, mass is the source of gravitational pull. The genius of Newtonian theory lies in the experimental discovery that inertial mass and gravitational mass are numerically equivalent. While Newton could not explain why this was the case, this equivalence became a crucial foundation for the later birth of general relativity, hinting at a deep, hidden connection between mass and the fabric of the universe itself. In our daily lives, we measure mass using scales or balances. A balance works by comparing an unknown mass to a standard one within a gravitational field, making it an accurate tool regardless of where you are, because it compares mass itself rather than weight. A spring scale, however, measures the pull of gravity on an object, which we call weight. Because gravity varies, being much weaker on the Moon, for instance, a spring scale's reading changes depending on your location. For a long time, the standard for a kilogram was a physical platinum iridium cylinder kept in a vault in France. But physical objects can change over time due to wear or contamination. To achieve higher precision, the international community redefined the kilogram in 2019, linking it to the Planck constant. This shifted our definition from a shifting physical object to a stable, universal constant of nature. Despite the triumphs of classical physics, it had limitations. Newton assumed gravity acted instantaneously across any distance, which contradicts the principle that nothing, not even information, can travel faster than the speed of light. This tension remained unresolved until Albert Einstein entered the scene in the early 20th century. Einstein's special relativity introduced the world to the idea that mass and energy are not distinct entities but two sides of the same coin. His famous equation, energy equals mass times the speed of light squared, revealed that mass is an incredibly concentrated form of energy. This principle explains the immense power released in nuclear reactions and is demonstrated daily in particle accelerators, where pure energy can be transformed into new, high-mass particles. Einstein then went further with general relativity, reimagining gravity not as a force, but as the curvature of space and time. He proposed that any object with mass or energy warps the geometry of the universe, much like a heavy ball creates a dip in a stretched rubber sheet. Other objects, and even light, simply follow the curves created by this warping. This theory predicted phenomena like gravitational lensing, where light from distant stars is bent by the gravity of massive objects, and the existence of black holes, where the curvature is so intense that nothing can escape. The recent detection of gravitational waves ripples in the fabric of space-time caused by colliding black holes has further cemented Einstein's vision as the bedrock of modern cosmology. As we move from the cosmic scale into the quantum realm, the mystery of mass deepens further. In the standard model of particle physics, we ask why some particles like quarks have mass while others, like photons, have none at all. The answer lies in the Higgs mechanism. The theory suggests that an invisible energy field, the Higgs field, permeates the entire universe like a vast cosmic ocean. As particles move through this field, they interact with it. Some pass through easily and remain massless, while others face a kind of resistance, gaining mass in the process. The discovery of the Higgs boson at the Large Hadron Collider in 2012 was a landmark achievement, confirming the existence of this field and providing the final piece of the Standard Model puzzle. Yet, even with this discovery, we are only at the beginning. As we look toward the future, exploring dark matter and theories beyond the Standard Model, we continue to seek a more unified understanding of how mass truly shapes the past, present, and future of our extraordinary universe. The discovery of the Higgs boson did not just confirm the validity of the Higgs mechanism, it provided a solid theoretical foundation for our understanding of how all elementary particles in the universe acquire their mass. However, while the Higgs mechanism explains the origin of mass for fundamental particles, it is not the source of all the mass found in nucleons, the protons and neutrons that make up the atomic nucleus. In fact, the mass that the Higgs mechanism grants to the quarks inside a proton or neutron accounts for only a tiny fraction of their total mass, perhaps only a few percent. So, where does the vast majority of the mass in protons and neutrons come from? The answer lies in the strong interaction between quarks and gluons, known as the strong nuclear force. Protons and neutrons are composed of three quarks held tightly together by elementary particles called gluons, which carry the strong force. The energy generated by this interaction is immense, and according to Einstein's principle of mass-energy equivalence, energy can be manifested as mass. Therefore, most of the mass of protons and neutrons actually stems from the intense binding energy between the quarks and gluons inside them. This energy is locked within the nucleon and expresses itself as mass, once again proving Einstein's great prediction that mass and energy are simply different manifestations of the same thing. Even at the quantum scale, this transformation is constantly occurring and is the key reason why everyday matter exists. From the more abstract perspective of quantum field theory, mass can be understood as the energy of the excited states of quantum fields. In this framework, every fundamental particle corresponds to a quantum field that permeates the entire universe. For instance, the electron corresponds to the electron field, and the photon corresponds to the electromagnetic field. When these fields are excited, particles are produced, and the mass of a particle is essentially a reflection of the energy required to create that excitation. The Higgs field plays a unique role here. By interacting with certain other quantum fields, it allows their excited states to possess a non-zero rest mass. This implies that mass is not an inherent, unchangeable property of a particle, but rather the result of the particle's interaction with its environment, specifically the Higgs field. This profound insight elevates our understanding of the origin of mass from a simple physical attribute to a concept deeply intertwined with the fundamental structure and interactions of the universe. Deepening our study of the Higgs mechanism and quantum field theory not only helps us understand the composition of matter but also provides vital clues for exploring deeper mysteries, such as the nature of dark matter and dark energy. When we shift our gaze from microscopic particles to the vast reaches of deep space, the mystery of mass does not disappear. Instead, it reappears in a much grander and more mysterious form. In the mid-20th century, astronomers observing galaxies and galaxy clusters began to notice baffling phenomena that suggested the existence of a massive amount of missing mass in the universe. This mass cannot be seen directly with telescopes, yet it silently governs the structure and evolution of the cosmos through its gravitational effects. One of the most famous pieces of evidence is the anomaly in galactic rotation curves. According to the laws of gravitation, if the mass of a galaxy were concentrated in its center, the orbital speeds of stars at the edge should decrease as they get further away, much like planets further from the Sun move slower. However, observations of spiral galaxies show that stars and gas clouds at the outer edges move far faster than expected, maintaining high speeds even at great distances from the center. These flat rotation curves indicate that there must be some invisible substance beyond the visible matter providing the extra gravity needed to keep these stars from flying away. Beyond galactic rotations, observations of galaxy clusters, the largest gravitationally bound structures in the universe, provide similar proof. By studying how these clusters bend background light through gravitational lensing, astronomers found that the total mass of a cluster far exceeds the sum of its visible stars and hot gases. This powerful lensing effect can only be explained if there is a vast amount of invisible matter present. Furthermore, the formation of the large-scale structure of the universe requires this missing mass. According to the Big Bang theory, the early universe was quite uniform, but gravity caused small density fluctuations to evolve into the galaxies and filaments we see today. If only ordinary matter existed, gravity would not have been strong enough to form such massive structures within the current age of the universe. All this evidence points to the same conclusion: the existence of a mysterious substance that does not emit, absorb, or reflect light, which we call dark matter. Dark matter, as the name implies, does not interact with electromagnetic radiation. We cannot see it, it produces no heat, and it does not form stars or planets. We only know it is there because of its gravity. Despite being invisible, its presence in the universe far outweighs the ordinary matter we are familiar with. Latest cosmological observations suggest that dark matter makes up about 27% of the total mass energy of the universe, while the ordinary matter we see, stars, planets, and gas, makes up only about 5%. What exactly is dark matter? This remains one of the greatest unsolved mysteries in modern physics. Scientists have proposed several theoretical candidates, the most prominent being weakly interacting massive particles, or WIMPs. These particles are thought to have significant mass but only interact with ordinary matter through gravity and the weak nuclear force, making them extremely difficult to detect. Other candidates include axions and sterile neutrinos. To unveil the mystery, scientists worldwide are conducting rigorous experiments, often building large detectors deep underground to shield them from cosmic rays and background noise. Some experiments use liquid xenon or crystals, hoping that a dark matter particle passing through will occasionally collide with an atomic nucleus and produce a tiny, detectable signal. Other strategies involve indirect detection, searching for gamma rays, neutrinos, or antimatter particles produced when dark matter particles annihilate or decay in space. Additionally, at high-energy accelerators like the Large Hadron Collider, scientists try to create dark matter particles directly in the lab, looking for signs of missing energy and momentum after collisions. Despite these massive efforts, no experiment has directly detected a dark matter particle yet, leaving its nature an open scientific puzzle. If dark matter is the missing source of gravity, then dark energy is an even more confounding component, acting as a kind of anti-gravity that drives the accelerated expansion of the universe. In the late 20th century, astronomers observing distant Type 1a supernovae which serve as standard candles for measuring distance found something unexpected. These distant supernovae were dimmer than predicted, meaning they were further away than they should have been. The only explanation was that the expansion of the universe is speeding up, rather than slowing down due to gravity. This discovery completely overturned our traditional understanding of the universe's fate and led to the concept of dark energy. Dark energy is thought to be a mysterious form of energy that permeates all of space, possessing a negative pressure that creates a repulsive force. Unlike dark matter, dark energy does not seem to cluster in specific areas but is spread uniformly throughout every corner of the cosmos. This discovery changed the map of the universe's composition fundamentally. Current models suggest the universe is roughly 68% dark energy, 27% dark matter, and a mere 5% ordinary matter. This means that everything we see and feel, all the stars, galaxies, and life, is just a tiny fraction of the total. Most of the universe is dominated by things we do not fully understand. Dark matter provides the gravitational scaffolding for galaxies to form, while dark energy dominates on the largest scales, pushing the universe apart and deciding its ultimate destiny. If the density of dark energy remains constant, the universe will expand forever until galaxies are isolated and even atoms are eventually torn apart in a scenario called the Big Rip. The exploration of mass is a never-ending journey. From Newton's classical descriptions to Einstein's curved spacetime, and from the Higgs mechanism to the mysteries of dark matter and dark energy, our understanding continues to deepen. However, even our most successful theories, the standard model of particle physics and general relativity, have significant limits. The standard model describes three of the fundamental forces and the particles they govern, but it fails to include gravity. Gravity's behavior at the quantum scale remains a massive question mark. We lack a theory of quantum gravity that perfectly unites the two worlds. Furthermore, the standard model cannot explain dark matter, dark energy, or the tiny masses of neutrinos. These puzzles push physicists to explore theories like grand unification, which suggests that all forces were once one in the early universe, or supersymmetry, which predicts that every known particle has a superpartner that could be a candidate for dark matter. Perhaps the most ambitious is string theory, which proposes that particles are not points but tiny vibrating strings in multiple dimensions. While mathematically beautiful, these theories lack direct experimental proof because the scales involved are so small. Other approaches like loop quantum gravity try to quantize space-time itself, suggesting it is made of discrete loops rather than being a continuous fabric. These quests all share a common goal: to find the ultimate origin of mass and the deepest laws of the universe. This journey, from the microscopic to the cosmic, is not just a scientific challenge but a profound human inquiry into the meaning of existence. As technology advances with better telescopes and detectors, we hope to one day lift the final veil. That is all for today's sharing. I hope you have sweet dreams, and I will see you in the next episode.